So, chemical manufacturing is the process through which a chemical is synthesized from raw materials and other feedstocks while optimizing their reaction conditions such as temperature, pressure, to get as much product as possible in the reaction mixture and to do so using minimum amount of energy. Even as we've known what a chemical manufacturing is, so it's important that we get to know what a chemical process is, because this is a combination of chemical reactions that are being accompanied when these raw materials are being turned into finished products. So they could include physical processes and some chemical processes. We have oxidation, hydration, crystallization, evaporation. These are just chemical processes that could be underwent when a raw material is being transformed to a finished product. And we also need to know what an industrial chemical plant is. The chemical plant is just an assemblage of apparatus which could be the provision of a reactor where the chemical reaction is taking place, the provision of heat exchangers that helps to regulate heat, and the provision of other materials, maybe some sort of grinders and some sort of milling section. So these are all assemblage of apparatus by which an industrial chemical process is realized. So this is what we term as industrial chemical plant. And this industrial chemical plant must be made in such a way in order to satisfy the requirements for temperature, pressure, filtration, let's say drying, extraction, etc. So these are just some of which should be really considered when setting up an industrial chemical plant, the assemblage. So chemical process technology has to do with the industrial processes in which raw materials are changed into useful product. So it's a technology. This is more like chemical manufacturing. So a chemical engineer or a chemical technologist must develop, must design, must engineer both the complete process and the equipment to be used. He must be able to choose the proper raw material. He must be able to operate the plant safely, and not just safely, efficiently and economically, and also to ensure that the finished product satisfies the consumers. This is the technology. So this is the work of a technologist or an engineer to ensure that the finished product satisfy the final consumers. So, in order for a chemical technologist or a chemical engineer or an industrial chemist to develop and choose proper raw material, design and engineer both the complete process and equipment used, and to operate the plant, as we said before, industrial chemical plant efficiently, safely and economically, and to see that the product meets the requirements set by consumers. These factors really has to be considered. And the first is that you have to look at the economic advantage to be gained in such a venture, from making that choice. And this economic advantage incorporates the availability of raw materials, the cost, logistics, facilities for the provision of the raw materials itself, and most importantly, the existence of market demand for such a product, because you can't go into the production of a particular product without knowing if this is really wanted by the final consumers. So this is economic advantage to be gained. You have to look at the economic advantage. And secondly, you have to look at the compatibility of the projected production within the plant environment. How compatible is what you want to produce within that location you've cited your industrial chemical plant? Because someone that is producing, let's say, cement cannot cite his industry where banks are located. You cannot have an industrial chemical plant that produces cement close to banks, you see. So it has to be very compatible within the plant environment. And you also have to consider the structural and maintenance requirements. How are you going to make it such a way to design your industrial chemical plant in such a way that it could allow for more expansion? And how are you going to maintain the assemblages? We've talked about the assemblages as to the industrial chemical plant, which has to do with the reactors, the dryers, the grinders, and the rest. So you have to look at the structural and maintenance requirement. You also have to look at the choice of a process technology, which has to do with getting to know the physical chemical conditions of the raw materials. Are you collecting them as wet or dry? So what are the physical chemical conditions to be observed from these raw materials, which will actually tell you whether the productivity or the productive activity is to be in batch. You have to look at it if it's going to be in batch or a continuous process. And if it's going to be in batch, that means you need a batch reactor. If it's going to be a continuous process, then you're going to need a continuous reactor. So the reactor is just the system where the chemical reactions take place. So you have to look at the process technology by looking at first the physical chemical conditions of the raw materials. All right, and that will determine what reactors could be used to satisfy those conditions. And that is also based on if you're going for a continuous process, that could be actually based on the market demand. If the market demand is so high, you need a continuous reactor, which has to do with production 24/7 in order to meet market demand, just like we have it as in the crude oil exploration. Okay, and this is actually done to maximize profit, which could actually lead to either reduction or increase in manual labor. So you have to also put into consideration where to site the plant. So where to site the plant, the industrial chemical plant, you have to look into the availability of raw material. You have to consider that too, alongside the availability of water, the availability of electricity, which is energy. And you have to also consider the attitude of the authorities towards disposal of effluent. And you have to also look at the availability of local labor force to provide faster social services to the community at large. So the site has to be properly situated. And another thing to consider is the unit operations. Okay, the unit operations, how are these individual units? Let's say grinding, let's say the reactor unit where the chemical reaction is taking place. How are they operating? So the unit operations are largely used to conduct primarily physical steps of preparing the reactants and controlling energy flow in and out of the chemical reactor, such as separating and purifying the product and possibly recycling the product or the reactant. All right, and that we can actually see in the production of ammonia. The product, some of the excess product or excess unwanted materials, or some of the excesses are being recycled back into the system. And that's talking about the unconverted reactants. So another factor to look at is the choice for the dimension. How large is it going to be? So you have to make choice for the dimension of the industrial chemical plant. So, and it's actually made on the basis of forecast sales of the product. It's over the years you might be like, okay, fine, in the next 3 years there's going to be expansion, so you have to make room for further expansion. So the choice of dimension should be flexible to accommodate more productive capacity of the plant due to the increased volume of sales. Okay, and this would actually help in reaching the full productive capacity of the plant. And in a case there were installation of some basic apparatus, so they have to be done to also accommodate an extension or addition of more, all right, due to increased demand or productivity as foreseen. So, and finally, a chemical technologist should look into the reactor design. So, the engineer has to look at the reactor design. So, in order to set up this chemical plant, you have to look at the reactor designs. So, and the type of reactor to be used and its method of operation has to be put into consideration. And the type of reactor could be batch or continuous or a hybrid of the two. And the operation could be, isothermal, it could be adiabatic in some intermediate manner. So depending on that, you could actually look at the physical chemical conditions of the reactant at the reactor inlet. And then you could actually look at the size, what's going to be the old size of the reactor and its configuration and dimension of any internal structures and all of that. So you have to also look at the exact composition and physical conditions of the product emerging from the reactor, the operating pressure, just to optimize it. All this has to be looked into as part of the reactor design. So, in an industrial process or in an industry, we want sustainable development. That means using the product as efficiently as possible to minimize use of energy and to minimize waste products. Okay, and we can actually optimize the reaction conditions to get as much product as possible in the reaction mixture, and to do so using very much minimum amount of energy. All right, and the things we need to consider are temperature, pressure, the removal of products as soon as they are formed, and the use of catalyst. Now we will take a look at the Haber process. That's the for the production of ammonia. Now, if you look at the equation of reaction, general equation of reaction, you will see nitrogen, hydrogen, ammonia being produced. 1:3 ratios. So, the raw materials being nitrogen is obtained from the air by fractional distillation of air actually, and hydrogen, which is mainly obtained from the cracking of hydrocarbons or from natural gas and steam. Now, the conditions for such a reaction requires that an ion catalyst is needed, and temperature of about 450 degrees Celsius and pressure of about 200 atmosphere is quite a high pressure. Okay, but looking at the equation of reaction, you can see the energy changes in the reversible reaction. We can see that is a reversible reaction. So now reversible reactions are actually um, exothermic in one direction and endothermic in the other direction. Exothermic in the first direction means that it is giving out heat, and it is endothermic in the other direction because it is taking in heat. So the amount of heat energy given out in one direction is the amount of heat energy taken in the other direction. Now, what are the uses of ammonia anyways? We make use of ammonia for making nitric acid and for the manufacture of products such as fertilizers, explosives, dyes, and medicine. So we want to actually know how the Haber process works. Okay, so we have our nitrogen, as we've stated earlier, from fractional distillation of air. All right, and we have hydrogen, all right, from cracking. So what happens is that these two are fed into a reactor. All right, we'll be talking about reactor in more detail in the next lecture. So once they're fed into the reactor, the reactant passes over ion catalyst at the stipulated temperature and pressure. Okay, once the process is complete, the product is cooled and condensed. So the condensed product, which is ammonia, is removed as liquid because it's going to condense, turned and liquefied. So after cooling, it gets liquefied and then it's removed as liquid. Then the unreacted gases are then recycled back into the system and the process continues. So in this process, the reactants are used efficiently, they are not wasted. So, and the energy used to make the reactant is not wasted, and thereby making us to have a reasonable yield of ammonia and to make it as quickly as possible. So now the question is, why use a temperature of 450 degrees Celsius for the Haber process? All right. So to answer this question, you have to look at it that heat energy is given out when ammonia is formed, right? Now, the forward reaction is exothermic, right? Increase in temperature, right? So it is exothermic in the sense that heat is given out of the system. So it then means that if we do the reaction at a temperature lower than 450, right, then we should get more ammonia in the reaction mixture at equilibrium. But the reaction is too slow at low temperatures. So we therefore use a moderate temperature as a compromise in order to make ammonia quickly enough to be economical. So we also use a catalyst to speed up the reaction rather than more heat. So the process is more energy efficient and the catalyst has no effect on percentage conversion. Why use a pressure of about 200 atmosphere? We know this is very high. Now, if you look at the equation of reaction for the Haber process, you get to see 4 moles of gas turned into 2 moles of gas when ammonia is formed. So we have less molecules of gas on the right hand side. So this means to support this, we have to actually look at it that if we carry out the reaction at high pressure, such as 200, then that means we will get more ammonia in the reaction mixture at equilibrium. Okay, and in addition, the rate of reaction will increase. And it's also important that you note that reversible reactions such as this does not go to completion, but it reaches a point of equilibrium. So at point of equilibrium tells us how much of the product we're having. Okay, so but high pressures actually take a lot of energy to create. So, and it requires greater safety precautions to prevent leaks or explosions. So we therefore use a moderately high pressure as a compromise, and that is why we make use of 200 atmosphere for the process. Let's look at the contact process for the manufacturing or for the production of sulfuric acid. The raw materials being sulfur and oxygen. Sulfur could be obtained from local refineries where it has been recovered from fossil fuels, that is oil and gas. So an oxygen could be obtained by drying and compressing air. So the conditions required for this process is the use of vanadium 5 oxide as catalyst, then a temperature of about 450 degrees Celsius, and a pressure of about 2 atmospheres. You can see just very low pressure when compared to that of the Haber process. So there are 3 stages to the process, to the contact process. The first stage is the making of sulfur dioxide. And usually sulfur that has been obtained is burnt in air to produce sulfur oxide. And the next stage is the making of sulfur trioxide. The sulfur dioxide that has been burnt is then heated in oxygen again to about 450 degrees Celsius with the vanadium 5 oxide as catalyst and the pressure at pressure of 2 atmospheres. So in that respect, an equilibrium is formed. Okay, now the next stage is the making of sulfuric acid. Now the sulfur trioxide undergoes through a series of reactions to form sulfuric acid, and you can see here the formation of oleum, and then the sulfuric acid that's been formed is further diluted to the concentration, to the required concentration. And what do we use sulfuric acid to do? Making of fertilizers such as ammonium sulfate, making of detergent, That includes shampoos, liquid soaps, and making of paint. Actually, it's used to extract the white pigment titanium oxide from its ores. So now, just as we've asked previously, why do we use a temperature of 450 degrees Celsius for the contact process? Now, looking at the equation of reaction, heat energy is given out when sulfur trioxide is formed. So the forward reaction is exothermic. Now, if we do the reaction at low temperature, that means we should get more sulfur trioxide in the reaction mixture because 450 degrees Celsius is actually low. The rate of reaction is too slow at low temperatures, okay? So we therefore use a moderate temperature as to 450 degrees Celsius as a compromise in order to make sulfur trioxide quickly enough to be economical. So we also use catalysts to speed up the reaction rather than more heat. So the process is more energy efficient. So why use a pressure of about 2 atmospheres? So looking at the equation of reaction, 3 moles of gas turned into 2 moles of gas when sulfur trioxide is formed. That means we have less molecules of gas on the right hand side. So if we carry out the reaction at high pressure, then we will get more sulfur trioxide in the reaction mixture at equilibrium. In addition, the rate of reaction will increase. So the conversion of sulfur 4 oxide to sulfur 6 is already so good in this case that a higher pressure than 2 atmospheres, which is quite low, is not needed, right? So the catalyst has no effect on the percentage conversion but helps to speed up the reaction as it will be too slow to be economically viable without it. So an alternative raw material for sulfur is the use of iron pyrite, which is an ore. And that could be obtained, we could actually obtain sulfur oxide by burning the iron pyrite in excess air to produce the sulfur oxide. And once the sulfur dioxide has been made, then it can undergo the previous stages we've talked about earlier in the contact process.